Now that we know all of the limit laws, we can start to work on more complicated limits. For example, on the screen we have a limit of a function x minus 3 all divided by x squared minus 2x, and the limit is approaching 2 from the left. If we try direct substitution on this limit, we don't get an indeterminate form, but we do get a number that's undefined. We get a non-zero numerator, and we get a 0 denominator. And that's one of the major rules in math, no dividing by 0. So we don't quite have an answer through direct substitution, but that result is an indicator of what to do next. If you come across a limit that has the form constant, a non-zero constant in the numerator, divided by a 0 in the denominator, what we need to do is factor out the cause for the 0 in the denominator. We're going to take our function and factor it in the denominator especially, and look for which of the factors is causing that 0 to occur. We can see that if x is equal to 0, our denominator will be 0, or when x is equal to 2, our denominator will be 0. In this case, the x equals 0 factor isn't causing a problem because our limit is approaching 2, it's not approaching 0. So it's that x minus 2 factor that's causing the 0 in the denominator. We want to separate that from the rest of the factors in the function. We're taking the numerator x minus 3 and grouping it with that factor x that's not causing any problems, and we're isolating the 1 over x minus 2 factor because that is what's giving us the 0 in the denominator, causing this to be undefined. We're going to return to our limit. As we've factored the function, we can now apply the limit law that says the limit of a product is the product of the limits. And we're going to evaluate each limit separately. Now this first limit, x minus 3 over x, when x is approaching 2 from the left, we can solve that using direct substitution. It's the second limit that really gives us the trouble because we know that one is going to give us 1 on top, but a 0 in the denominator. But we have a theorem for functions that follow this format. Recall that if we have a function that looks like 1 over the binomial x minus a raised to the power of n, and our limit approaches a, which is essentially where our vertical asymptote occurs, that we have two cases. Either the exponent is even, or the exponent is odd. Now here, we don't really see an exponent in the denominator, but it's assumed that it's a invisible 1 as the exponent on the binomial x minus 2 for our function. So we have an odd exponent, which means our function behavior, it's opposite on either side of the asymptote. And if we're coming from the left, we know that that limit is heading down to negative infinity. With these two limits evaluated separately, we can now bring them back together and think about what that product would entail. We have a negative 1/2, but then we have a negative infinity. The two negatives together you can think of as opposite opposite. So we started with a negative 1/2, but then we applied an opposite from the negative infinity, meaning we're now going up instead of down. And then if we think about multiplying something like 1/2 to something that's infinite, the infinite wins. So the product of negative 1/2 and negative infinity, we're not actually multiplying those two numbers, technically, but we're thinking about what happens when those two limits collide and they turn us around to positive infinity. So the limit that we were trying to evaluate, x minus 3 divided by x squared minus 2x, when x is approaching 2 from the left, it's going to positive infinity. Now, we could see various versions of this same type of problem. Maybe instead of our limit approaching 2 from the left, it was approaching from the right. That would change things a little bit, because when it comes down to evaluating that limit using the theorem for functions that have the vertical asymptotes, instead of coming from the left, we'd imagine coming from the right. Or say our function was a little bit different, and in the denominator, that factor that's causing the 0 has an exponent that's even rather than odd. Then we would use that theorem again for the functions that have vertical asymptotes, and we would say, well, even functions behave the same on both sides of the asymptote, so it doesn't matter if you're coming from the left or the right, it would be going up to positive infinity for that factor of the function. So when you're evaluating limits that take this form, k over 0, you're going to factor out the problem in the denominator. Find the part that's causing the 0, factor that off, apply the theorem for that factor, and then apply the limit to the rest of it. You can do direct substitution for the remaining portion of the function, and then bring the two together. If it's negative and negative, then you know those two combine to be positive. If it's one negative with one positive, that would stay negative. But you're going to evaluate the limits separately and then bring the product back together.